All right, now that we know the requirements and the calculator function, let's do some examples. So in the word problems, example number 3. When she was 9 years of age, Emily Rosa did a science fair experiment in which she tested professional touch therapists to see if they could sense her energy fields. She flipped a coin to select her right hand or her left hand. Then she asked the therapist to identify the selected hand by placing their hand just under Emily's without seeing it, and without touching it. Among 280 trials, touch therapists were correct 123 times. So, given that Emily Rosa used a coin toss to select her left or right hand, what proportion of correct responses would be expected if the touch therapists were just making it up? So, since Emily used a coin, what would we expect that, if they're just making it up, what would we expect the probability to be of them getting it right? Well, it'd be the same as getting a coin flip right, correct? So, that's just 1 out of 2, which would be 50%. So, if we get a confidence interval that surrounds 50%, then they're probably making it up. We would need to get a confidence interval, right, for all touch therapists. Remember, this is just a sample. We need to get it for all touch therapists. Would have to be bigger than 50%. So that's the goal. That's what we're going to end up hopefully going to see. All right. Part B, what is the best point estimate of the therapist success rate? So remember, point estimate is your sample. So since we're trying to find a population proportion, it's going to be the sample proportion, right? And sample proportion is just a fancy word for probability. So we do the number of successes, which are the number of times they were correct, 123, divide by 2080, and we see that we get about 0.439. All right, part C. Using her results, construct a confidence interval estimate of the proportion of correct responses made by touch therapists. So it tells us a confidence interval to estimate the proportion. So we know we're going to be doing 1 prop z int. But first, let's make sure that we actually can do this. Are the requirements all met? Well, number 1, it has to be simple random. So she said she's didn't say how she's selecting her people, but it did say that she's doing it pretty randomly. So we could probably just assume at the very least. We can assume that the way she got her touch therapist was by a simple random sample. Number 2, are there 2 outcomes? Yes, they either get it correct or they get it incorrect, right? Correct or incorrect. Another way you can think about it is either the right or left hand. So 2 options. Number 3 was independent events. Right? So we can see that each individual should be independent, right? Also, each time she's flipping a coin, right? So even within that, they would be independent of each other. One coin flip to another coin flip doesn't affect each other. So these are independent. And then lastly, we got to check that formula. So we get n times p hat times 1 minus p hat. So n this time is 280. So we get 280 times p hat, which we said was 123 over 280, times 1 minus 123 over 280. We multiply these all together. We see that we get about 68.967, which is definitely above 10%, above 10. So also great. All right, so all these work, so we can do 1 prop z interval. All right, so into 1 prop z int, we have x. X is the number of successes. It has to be a whole number, so the number of correct times they got it was 123. N is going to be 280. The C level, so that's the confidence level, right? Which we can see right there is going to be 99%, so we just do 0.99, put it in its decimal form. So at the very top, when you hit enter, you should see 0.363, 0.516. And that's going to be our confidence interval. So remember, this was for our sample. This is for the population. So this is all touch therapists. So, do the results suggest that the ability of touch therapists to select the correct hand by sensing energy fields? Can they actually do this? Well, what did we say? Remember from the part B, or part A, we said that they have about a 50% chance of getting it correct just by guessing. If they were correct, we would need them to be completely above it, right? We would need the proportion to be higher. It would need to be 70% or 90% or something like that, right? But if we look at our confidence interval, we have 0.363 and we have 0.516, right? And 0.5 is right in between there. So the entire interval is not above 0.5, right? 0.5 is within this interval, so we can kind of assume it is 0.5. If we look at all the different possibilities between these two values, right, we could even have something smaller. It could be 0.4. It could be 0.6, right? Regardless, since the entire interval is not above it, it's not going to be better than that. So what do this suggest? They suggest that touch therapists are probably just making it up. Because 0.5 was inside the confidence interval. All right, let's look at a few more examples so that we can get our heads around those kinds of concepts. A Consumers Report Research Center survey of 427 women showed that 29% of them purchase books online. So what number of women purchase books online? So it's 29% of 427, so we can just multiply that out, and we get 123.83. However, can you have 0.83 of a woman? No, that doesn't make any sense, right? So we just round normally, so that would just be 124 women. So part B, find the 95% confidence interval estimate of the percentage of women who purchase books online. So it says interval and percentage. So we're going to do 1 prop z int. But again, let's just look at our requirements. Make sure all the requirements work. So it didn't tell us how they got all these women, so we can just assume it's simple random. All right. Are there two options, two qualitative options? So it shows whether they purchase books online. So either they purchase books or they don't, right? Those are the two options. All right, let's take a look at this. So we said either independent or we can do that formula. Let's look at the formula, right? So remember, the formula says that n is less than or equal to 5% of your population. So another way to think about that is your sample. What is our sample in this case? Hopefully we said it was the 427 women. So is that less than 5% of all women? Yeah, right? That makes sense. There's way more than, this is going to be way more than just 5%. Or sorry, way less than just 5%. If you want hard numbers, what we can do is we can actually do 427 divided by 0.05. And when we do that, we end up with 8,540. And since there are way more than 8,540 women in general, right? We know that our sample size is definitely less than 5%. So that totally works. Lastly, we need to just check our formula. So N, we said, was 427. P hat is 29%, so 0.29. And then 1 minus 0.29. We type all that into the calculator. We end up with 87.92, which is definitely bigger than 10. All right, so all the requirements are met. So let's do one prop z int. So we see x is going to be 124, right? It's a whole number. We already figured that out from part A. N is 427. The sea level is 0.95. So when we hit enter, we end up seeing 0.24734 and 0.33345. But since it said percentage, right, we want to make sure to put that in percentage form. So another way we could write that is that our value is between 24.7% and 33.3%. So this is another way to write it, right? Here's our low value, here's our high value. And our population proportion is right there in the middle. So, can we safely conclude that less than 50% of all women purchase books online? So, again, remember it's all women, so we can't look at this number. This is just of our sample of women. We need to look at all women. So, because of that, we need to look at our confidence interval. So our confidence interval, if you drew it on a number line, right, it would be 24.7%, 33.3%, and we know that the proportion should be somewhere between these two numbers. So where do we see 50%? 50% is way out here on the outside, right? So can we safely conclude that less than 50% of women purchase books online? Well, remember that the percentage of women who purchase books online have to be between these two numbers, right? The low and the high. So what could it be? What's the number between 24.7 and 33.3? Well, we see that it could be 30%, right? 30% of women could purchase books online. 32% of women could purchase books online, 33.1%, 25%, right? All these different types of answers. So are all of these numbers less than 50? Yeah, the entire confidence interval is less than 50. So can we safely conclude that less than 50% of women purchase books online? Yeah, any number between these two numbers are going to be less than 50. So we could say yes, because the entire confidence interval is less than 50%. Can we safely conclude that at least 25% of all women purchase books online? So since it's all women, right, we got to look at our confidence interval. So confidence interval goes from 24.7% up to 33.3%. So any value between here. So where is our 25%? It's inside. So is any value between here, because remember, we don't know where the population is. We just know it's somewhere between these two numbers. So is every possibility between these two numbers at least 25? Well, sure, it's true that if P was 30% or 28% or even 25%, that it would be at least 25. But isn't it also possible that P could be 24.8% or 24.9%? Are those at least 25? No, right? So since these are a possibility, right, we cannot conclude that at least 25% of women can purchase books online. So another way to say that is no, because 24.8% could be the proportion, right? Which is less than 25. Or you could say, so that's one way you could say it. You could also say no, because 25% is within the confidence interval. So, what are some things that we could safely conclude? So, let's have another thing. So, if we have confidence intervals that go 24.7% up to 33.3%, what are some other things that we could conclude? So, we could conclude that more than 24% purchase books online, right? Because if we put 24 on this number line, it's less than that. All of the numbers between these two are more than 24. We could say at least 16%, right? 16% is way down here. Anything, all of these values are more than it, so at least 16 would also work. Could we say that less than 23% purchase books online? Could we say that? So 23 would definitely be down here. But if you notice, all of the values within the confidence interval are above it. It's actually more than 23, not less than. So no, we couldn't say that. But we could just change it to more than, and that would be okay. All right, hopefully this is starting to make sense. Let's look at a couple more examples. A Pew Research Center poll of 1,007 randomly selected adults showed that 85% knew what Twitter was. Find a 95% confidence interval estimate of the population proportion. So, confidence interval, proportion. We know we're doing one prop, z-int. But before we do that, remember we gotta always do the requirements. So, it doesn't tell us how they got it. It just says randomly, so we can just assume simple random. Are there two outcomes? Yeah. They either know what Twitter is or they don't. All right, let's look at our sample size formula, right? Is the sample size less than 5% of the population? Well, 1,007 is definitely going to be less than 5% of everybody, right? The other way you can do that, if you want the hard number, not just the feeling, if you divide it by 5%, we see that we get 20,140, which there's definitely more than that many people, right? In all of the world, or in all of the nation, there's more than 20,000. So yeah, our sample size is definitely less than 5%. And then we get our weird formula. So we said N was 1,007. P hat is going to be 85 or 0.85. And then 1 minus 0.85. So when we plug that into the calculator, we should get about 128.39, which is definitely bigger than 10. All the requirements check out. So let's go back to the one prop z-int. X is going to be what? So it's not 85, because 85 is a percent. And remember, X is a number. So we need to figure out if 85% of 1,007 responded, how many people is that? So we can do 0.85 times 1,007, and we get 855.95, right, which rounds up to 856, because we need whole numbers. So that's what our x is. It's 856. N is going to be 1,007, and then sea level is going to be 0.95. So here's also a hint. If you actually wrote 855.95, it's going to give you an error. And the error is because x is a whole number, right? You can't have 0.95 of a person. So you need to make sure to have that whole number, otherwise you will result in an error. But having the whole number, when we plug it in, we end up seeing that our confidence interval is 0.828, 0.872. So part B, find the margin of error that corresponds to the 95% confidence level. So remember our confidence level. Remember the way we find it, we already talked about this. The low number is p hat minus e. The top number is p hat plus e. Right? So we can just do p hat minus the low number. Right? Because that's how far away the low number is from p hat. It's just e. And when we do that, we get 0.85 minus 0.828, and we get 0.022. So 0.022 is our answer. We can also do it the other way, but once you have it once, you don't have to do it both times. So you could also do high minus p hat, and you end up with the same answer. So based on these results, can we safely conclude that more than 75% of adults know what Twitter is? So these are all adults. This is not just our sample of 1,007, so we have to look at our confidence interval. So our confidence interval goes from 0.828 all the way to 0.872, right? So where's our 75%? That's going to be way down here. Is it true that all the numbers in our confidence interval are more than 75%? Yeah. So we can just say yes, because the entire confidence interval is more than 0.75. Good. All right. So let's do something a little different, a little more theoretical. So what happens to a confidence interval if you decrease the confidence level? What happens to the confidence interval if you decrease the confidence level? What happens to the margin of error? Okay, so let's actually go back and let's check using example number 5. So number 5, example problem 5, we used a 95% confidence interval. So let's just decrease that. Let's decrease that level to 80%. So we're going to go down to 80% confidence. So let's just redo the whole problem. So not the whole thing. We don't have to do we don't have to prove the requirements because it's the same problem. So x is the same thing, right? N is the same thing. The only thing that changes is the sea level, which is 0.8. So when we hit enter, what we see is we get 0.835 and 0.864. So with 95% confidence, we ended up with 0.828 and 0.872. So what happened when we decreased the confidence level? What happened to the confidence interval? We see that it narrowed, right? Because if we labeled on the chart, right, the 95% would be 0.828, 0.872, And then the 80% would be 0.835 and 0.864. All right, so less confidence narrowed our value. Now let's think about that. Why would that be the case? Well, let's talk about a silly example. Okay, so let's answer that question from the beginning of the lesson. How many Americans have seen Titanic? Well, I can tell you that I am 100% confident that that number is between 0% and 100%, right? I am 100% confident. And I can tell you that because I have not seen Titanic and my roommate has. So I am 100% confident it's between 0 and 100. Now, why is that a stupid thing to say? Why is that not all that helpful? Because most probabilities are between 0 and 100%, right? Between 0 and 1. So that doesn't actually help anything. It doesn't narrow anything down for us. So I could narrow this down. I could narrow this interval down to 1% and 99%, right? But now I'm not 100% confident anymore. My confidence has decreased. Now, I don't know what it would have decreased to, but it definitely can't be 100%, right? Because remember, 100% is certain, and I'm no longer certain, right? It's possible that 99.7% of people have seen Titanic, or that 0.05% of people have seen Titanic. I don't know. Probably not. But I can't say for absolute certainty anymore. So when you narrow your confidence interval, you're gonna be less likely, or you're gonna be less sure about that your actual probability is between those two values. All right, hopefully that made sense. So the confidence interval narrows when you decrease your confidence level. What happens to the margin of error? Well, remember, the margin of error is the value that you are subtracting and adding, right? So at 95% versus 80%, can we see what happens to the margin of error? Do we see how it gets smaller, right? 95% is way bigger margin of error than the 80%. So we see that E decreases as well. So if the confidence level decreases, the margin of error also decreases, and the confidence interval narrows. All right, let's look at part B. What happens to the margin of error if you decrease the sample size? So let's go back and check with problem 5 again. And this time, instead of 1,000 people, let's just say it's 100 respondents. So it's 85% of people, 100 respondents. So we got one prop z int x. This time it can't be 800 because we only have 100 people. So we can do 0.85 times 100, which is just 85. So x is 85. N is 100, and we'll keep the same C level. We don't want to change too many things. So we'll keep it at the original 95%. And what you see is that you get 0.765 and 0.914. So what happened to the confidence interval? We see that the confidence interval widened, right? Because the original one was 0.828, 0.872, and we see that now it's 0.765, 0.914. And since the confidence interval widened, right, that means that the margin of error increased. Right? Because originally it went only this far, but now it goes even further. When the confidence interval widens, the margin of error increases. So this is what happens when you decrease the sample size. And the reason why is because you want big sample sizes. The bigger the sample size, the better all of your data will be. So here is a silly example. All right. So if I went to a school and I wanted to know the school suspension rate, and I just walk in the door and I talk to 3 people standing just in the hallway, walking in the hallway, and I say, hey, have you ever been suspended? Well, if all 3 people are coming from in-school suspension, then that's 3 out of 3 people. That's 100%. Oh my gosh, 100% of these students have been suspended. That's crazy. We got to pull funding. We got to get them better teachers, better computers, better everything, right? Well, no, of course not. You only talked to 3 people. That's too small of a sample. So we need to have a big enough sample. So the better, the more people you have in your sample, the more confident you can be that it is closer to the population, right? To the point where when you actually just ask everybody, you'd be 100% confident. Good. So a natural question would be, what's the cutoff point? So 3 is obviously a ridiculous number, but the entire population is also a ridiculous number, right? We can't necessarily talk to every single person in the country, in the world, whatever we're talking about, even in the county sometimes. So what number is in between here that's the cutoff that says, hey, this is a good number, that's statistically sound, that we can actually use? Well, that's going to be what the next section is. But before we get there, because it's going to be a formula, and the formula is going to scare you. So before we go there, let's just talk about something that's hopefully not going to be too scary. And then we can just digest these in little bits and parts. All right, critical value. So we got to go back to our normal section, normal distribution section, our z-score section. Now let's talk about critical value. So a critical value is a z-score. So we typically see it as z alpha. So, okay, now if you remember earlier, here's finally where that alpha might be coming from. So this is just a z-score that separates the top probability of alpha. So alpha is a probability. Also remember that z-scores have a mean, are normally distributed with a mean of 0 and a standard deviation of 1. Okay, so let's just write this out. So let's find the critical value. So the critical value of 0.05. So that means that it is the top 5%. So this is a probability, so we can just turn it into, that's in decimal form, so we can turn it into percentage form, right? So remember, we said we don't do top percentages, we do bottom percentages. So that's the same as the bottom 95%. So if we graph it, right, mean goes in the center, so that's 0. 95%, we go from the left. If we go up halfway, too far or not far enough? Well, halfway is half, so that's 50%, so not far enough, so we got to keep going. We shade everything to the left. And this percentage, remember percentage goes up, so this is the percentage, this is the value we're trying to find, right here. So, because we're trying to find the z-score, we do inverse norm, 0.95, comma 0, comma 1. And we end up with 1.645. All right, let's do another one. So let's find z alpha, where alpha is 0.32. So z alpha, or z of 0.32, the critical value of 0.32 means that it's the top 32%. But we don't like top percentages, we want bottom percentages. So that's the bottom 68%. So if we draw our graph, right in the center is 0. If we're going from the left up 50%, that's not far enough, so we got to keep going. Shading everything to the left. Remember, the percentage goes up, so that's going to be up here. Z-score is what we want, so we're going to do inverse norm. The area we have is 0.68, comma 0, comma 1. So our final answer is 0.47. All right, 2 more and then we'll get into our stuff. So this time, notice I didn't want the critical value of alpha. I want the critical value of alpha divided by 2. So if alpha is 0.12, we just need to divide it by 2 because that's what I want. So if we divide that by 2, we get 0.06. So the critical value of 0.06 means you have the top 6%. But again, we only care about the bottom percentages. So that's the bottom 94%. We graph it, right? Going from the left, 50% is not far enough, so we got to keep going. We put 94 here, and we're trying to find this probability, right? Hopefully you said no, right? This is the 0.94, and this is what we want, right? Data values, z-scores go on the bottom, percentages go up top. So to find this, we do inverse norm, 0.94, comma 0, comma 1, and we end up with 1.55. Hopefully you're also seeing a pattern, right? Once we figure out what that bottom percentage is, we're just plugging it into inverse norm with 0 and 1. Right? Once we figure out what the bottom percentage is, we're just plugging that into inverse norm. Bottom percentage, inverse norm, right? So, one more and then we'll move on. So, we have our critical value of alpha divided by 2 where alpha is 0.28. So, we don't care about alpha, we care about alpha divided by 2, so we just divide that by 2. Whoops. Well, that's annoying. There we go. All right, so we want the critical value of 0.14. So that is the top 14%, which means it's the bottom 86%. So we know, right, by doing this over and over again, the way we get the critical value is just doing inverse norm of 0.86, the bottom percentage, comma 0, comma 1, which is going to be 1.08. All right. So now we're going to answer that question about the sample size. So what is the sample size that is desired? So that way we have a statistically viable sample, right? We asked enough people. 3's not enough. Everybody's not reasonable. What number is the cutoff point? So a question that you may see is either find the sample size, or you could see the words how many, right? How many is an indicator that, oh, I need to be doing the sample size formula. And unfortunately, we do need to know the formula. You don't have to memorize it. I will give you the formula, but you definitely need to know how to use it. So critical value. So N is going to be that critical value that we've been working with squared times P hat times Q hat divided by E squared. So on a regular test, I would give this to you. So if you were taking a in-class test, this is what you're going to have. This is what I'm going to give you. All right, N is a sample size. P hat, we already said, that's the sample proportion. Q hat is just 1 minus P hat. So that's all that is, 1 minus P hat. E is going to be the margin of error. And then this is going to be the critical value of alpha divided by 2. So the only thing else we need to know is what's alpha. So remember, this whole time we've been talking about how confidence level is 1 minus alpha times 100%. And I said, don't worry about it. We'll get back to it. This is when we're finally at it. So alpha is just 1 minus your confidence level. So I would definitely suggest doing it in this order, making the critical value the last thing you do. Because again, this is going to mess up. If you round the critical value, you're going to have the wrong answer. So we want to make sure that we only round at the end of the problem. So 2 important things you need to know. When we don't have a p-hat, so if they don't give you a p-hat, you just assume 50%. So p-hat is 0.5, which means that q-hat, which is 1 minus p-hat, would be 1 minus 0.5, so that's just 0.5. So if you don't know p-hat, you just assume it's 50%. The other thing, you always round up. Always. This is the only time you always round up. It's when it's sample size problems. Every other time you round normally, right? This is the only time, and here's why. Because we're talking about minimum values. So if the minimum sample size you need is 89.1, well, if I ask 89 people, is this going to be statistically significant? No, because you need at least 89.1. So 89 is no good, which means that the whole number that I need to ask is 90. So that's why we always round up. All right, so let's look at some examples. So many companies are interested in knowing the percentage of adults who buy clothing online. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So it uses the word how many. So this is going to be a sample size problem. And it's talking about a percentage. So we know we're going to be using the proportion problem, or the proportion formula. Part A, use the results from a census that 66% of people buy clothing online. So we're going to use our formula. So p-hat is 66%, right? That's how many people buy clothing online. 0.66. Q-hat is just 1 minus 0.66, which is 0.34. Now the margin of error, we don't have to find it. It actually gave it to us, right? It wants to be an error by no more than 3 percentage points. So it's not 3, it's 3 percentage points. So that's 0.03. That's tricky. Make sure you catch that. 3 percentage points. So it'll be 0.03. You'll be off if you put 3. All right. So now let's just find our critical value, which we've been doing. It's easy, right? So alpha, we said, was 1 minus the confidence level. How confident do we want to be? This time we want to be 95% confident. So we do alpha is 1 minus 0.95, which is 0.05. But do we want alpha? No, we want alpha divided by 2. So we just divide all that by 2. And we get 0.025. So that means that we want the critical value of 0.025. So that's the top 2.5%, right? Which means it's the bottom 97.5%. So to find that critical value, we just into inverse norm, type 0.97501, and we end up with 1.95996 blah, 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 right? Now, you need to make sure to do the entire thing. If you don't do the entire thing, you will potentially get the wrong answer. So when we plug all of this back into our equation, right? So right now, hopefully, this is the giant number that's in your calculator. So all you need to do is just hit the square button, right? So it'll say, so in your calculator, you should say C answer squared, and then you can multiply that by p-hat, which is 0.66, multiply that by q-hat, which is 0.34, and then divide by 0.03, and then just square that number 2, and that should give you your answer. So if we looked at it on paper, this is what it would look like, right? So you should end up with 957.803, blah, blah, blah. But since we always round up, our answer is 958 adults. And that's our final answer. All right. So part B, same topic, same question, but this time assume that we have no prior information. So we're still going to use our formula. So p hat is 0.5 this time. Why? Because we don't have a p hat, right? They didn't tell us anything about a previous problem or a previous survey. So since p hat is 50%, q hat is also 50%. E is still 0.03. Our critical value is the same thing too, right? Just inverse norm, 0.975, comma 0, comma 1. It's that long number, 1.959, blah, 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 blah. So we can just plug that all back into our calculator. So it might be good just to, when I do problems like this, I just retype inverse norm to get that number back and nice in my calculator. So that way I can just square it, times 0.5 times 0.5 divided by 0.03 squared. And you should end up with 1067.07 blah, 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 blah. So we're just going to round that as normal to 1067, right? Hopefully not. Remember, we always round up. So it'd be 1067. And by that, I mean 1068. Good. All right, last problem. Find the sample size needed to estimate the percentage of Democrats who have tattoos. Use a margin of error of 0.05. Use a confidence level of 99%. And use results from a previous survey that said 15% of Democrats have tattoos. So find the sample size. So obviously it's a sample size problem. To estimate the percentage. So we know we're going to do our percentage problem or formula. All right, so p hat is 0.15. That's what they gave us. Q hat is 1 minus p hat, which is 0.85. E is 0.05. That's the margin of error. They told us that one too. All right, so last up, critical value. Remember, alpha is 1 minus your confidence level. Confidence level is 0.99. So 0.01. We don't care about alpha, care about alpha divided by 2. So just divide everything by 2. So we want the critical value of 0.005. So remember, that's not going to be the top 5%. That's going to be the top 0.5%, right? Moving that decimal over 2 places. So since it's the top 0.5%, that's going to be the bottom 99.5%, right? Because again, you can just do 100 minus 0.5. Or you can do 1 minus 0.005. End up with the same thing, right? Either 99.5% or 0.995%. Or 0.995, excuse me, not percent. All right. So, as always, since we already have the bottom percentage, we just do inverse norm, 0.995, comma 0, comma 1. We end up with 2.5758, blah, 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 blah. So, typing that into our formula, right, we want to square it. Then multiply by 0.15, multiply by 0.85, divide by 0.05 squared, and we end up with 338.379 blah blah blah, which of course is going to round up to 339 Democrats. All right, so let me know if you have any questions. Hopefully this is great though. So you all have a great day, and I will see you next time.